All right. Sorry for the delay. Let's quickly begin the session. So today we are here with a very interesting session that is a live webinar on a very interesting topic again, big data, managing the unmanageable. And today we have here with us Dr. Samiya Khan. So let me give a quick introduction of our speaker for today, and then we'll begin with the session. So Dr. Samiya Khan is currently working as a postdoctoral research fellow at University of Wolverhampton at United Kingdom. She has more than 15 research papers in her publications extend across various journal articles and book chapters in high impact publications of international repute. She has served as an associate at many reputed journals and conferences with IEEE transactions on emerging trends on computing and information processing and management. She is a contributor to magazines with many articles published in CSI Communications and Scientific India. Besides this, she has authored the book on big data and analytics and co-edited a book uh, on big data and analytics entitled Internet of Things, Concept and Applications, published by Springer, Nature, Switzerland. Dr. Samia's expertise span across data science, artificial intelligence, edge computers, and Internet of Things. Uh, she 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 has also expertise in healthcare, smart agriculture, where data acquired from IoT sensors is being used, AI models for descriptive, diagnostic, predictive, and prescriptive applications. So I'm glad to have you here, Dr. Samiya Khan, as a speaker for today. And participants, you feel free to share the link across your friends and connections. So let's quickly begin with the session. Over to you, Dr. Samiya.
Hi, thank you for the kind introduction. Do you mind if I share my screen? Okay. So is my screen visible to everyone? I can't really see any chat that comes in. So if someone can be kind enough to read the chat and let me know if there's something.
The screen is visible. You can go ahead.
Yeah, I was talking about the chat. So I can't see if somebody writes anything in the chat. So in case you can be kind enough to interrupt me if there's anything. Right? Okay, so thank you for the very kind introduction. Just to, to start, my name is Samiya, and I am a research fellow at the University of Wolverhampton. I've been here for almost 2 years now, and majorly been working in the use of artificial intelligence for Internet of Things applications, spanning across domains like healthcare and agriculture and manufacturing, for example. Now, my core area of expertise is big data. My PhD thesis was on big data and the use of big data analytics in the cloud environment. Which is when I actually started conceptualizing my book. I've been teaching, I taught in India for 2 semesters, to be precise, teaching big data. And which is when the whole interest around big data and writing book around it or pursuing research around it came about. So just to give you an overview of what I intend to cover as part of this presentation is we'll start with a bit of a background and the origin of where the whole thing about data science came about. Then we look at a few trends and what's the big deal about big data, kind of a question. We'll try and answer that. Then the characteristics and the process, which is like the more technical aspects of it. I'm not sure about the background of the participants who joined this webinar, so I'll keep it very generic and general. Finally, we'll just look at a few real-life use cases, some of the use cases that I've actually been working on in the past few years of me working in this area, which has been almost like 6-7 years now. So that's how it is. To start with, looking at the background and origins, now the use of big data, the use of data in general, recording data and using data to keep track of things or making predictions around it. It's very human. I mean, it's very. I remember. I mean, as a student, as a PhD student in my first year, I had attended a conference, which was, I mean, if I remember it correctly, it was CSI. It was Computer Society of India convention. And the very famous Professor K.K. Agarwal was the keynote speaker for that conference. And I remember him saying one thing, that computer science is all about common sense. So computer science is completely just common sense. That is where everything in computer science comes from. And when we come to data science, it doesn't change much in its theology or philosophy from that aspect. So we humans, I mean, if we look at artificial intelligence as well, it is much to do with how we process information, how we make predictions around it. So just to start with a quick example, if you go to the supermarket, I'm sure everyone goes to the supermarket once a week or so, maybe more than that. If you keep going to the same supermarket over and over, week again and again, you will automatically, process in your brain that, well, on these particular days, on these particular hours, the supermarket is busy, and I'll try not go to the supermarket during those timings or on those days. So that's data processing at the most naive level that we do in our brain. Now, recording information is something which is very limited in our case. In case of humans, we have an active memory and a passive memory, something that we can immediately remember things that we take time remembering. And there might some people are better at remembering things, others are not so good at remembering things. So the storage or the capability of maintaining the stack of information within our brain is rather limited, and that is why we require machines or pen and paper to write down things and remember them. Now, going back to when the whole concept of actually recording data onto something other than the human brain goes back thousands and thousands of years to the Mesopotamian civilization, which was when the whole concept of accounting actually started. Now, their use was very limited. It was to maintain the number of animals in their herd or the livestock that's there for a farm. That was the kind of information that they started recording. A more formal conceptualized approach to this came about in the year 1663, which was also many, many years ago, when a person called John Grant basically collected data and analyzed the mortality rolls in London. So that is kind of the first statistical project around collection of data and then analyzing it. Then as the amount of data that we were trying to process increased and it went beyond the limitations of human capacity or even the capacity of doing it on paper. For example, if you have to make, say, 10 calculations, you can write them down on the paper and you can do them. If you are very, very talented, you might be able to go on and do around 50 calculations onto some sets of numbers using pen and paper. But doing thousands or millions of calculations, it is going to be very, very challenging. So you need a machine to do it. You need maybe many people to do it. So the whole idea of a computing machine or a machine that could iteratively calculate something or process any kind of data or store that data and then process that data, the whole notion around this came about once the computing machine was invented. And that is, the whole idea of processing data from that perspective, that we can actually have statistical results from it came about more. I mean, it became more popular in the 20th century, which is why we refer to the 20th century as the information age. Now, if we just look at the timeline of how things have progressed over time in the 20th century, if we look at the first data project that was created, first formally known documented data project, that was in the year 1937. Then as machinery has evolved, as our capacity to store data, to process data has evolved, our capabilities of data processing have also evolved, and the whole thing about data science coming up as a completely new branch of science in itself has also come about. So if you see, most of the timeline covers inventions, the data processing machine, the building of the first data center, and then the whole thing about internet actually revolutionized everything, because now we need data processing capabilities all the more because of the kinds of data that we're collecting. So we're collecting immense amounts of data now. We're generating immense amounts of data now. And to be able to even understand whether you require any data or whether you need to archive it or you can filter it off, that also requires a huge amount of processing capability. So the advent of internet and the advent of social media has increased the amount of data that each person is generating. It has been humongous. So, I mean, that's perhaps why everyone says that the internet and mobile technology have been the two most path-breaking technologies in the history of computing, or in the history of technology as it is. Now, the capabilities ever since have improved, and I mean, something that each one of us relate to. I think I remember while I was in school, we used to use floppy drives to save the programs that we wrote and to show it to our teachers. And then as time progressed, people moved on to CDs, and then there were pen drives, and then now there are hard drives that are so small, and you can store like something like 2 TB of data in it. So the amount of data that you can store in the same, say, per square meter or per square centimeter space has increased immensely. So our capabilities have improved in terms of storage. Our capabilities have also improved in terms of processing ability. If any one of you, I don't know how many of you have seen the DOS machines that were used previously, to the i7s that we use now, the processing capabilities have by far, exceeded the limits of what people could have imagined back then as well. So the whole idea of giving data science the magnitude and the magnanimity that it has today goes, and a lot of credit of that goes to the advances in storage and processing technologies in the past few years. Now, going back into the history of big data as it is, and when it actually came about. So the term why 2005? Because we actually did not have a lot of digitalized data until very recently. So the whole projects that governments have been running around digitization of data that is collected across the country, across cities, across villages, across counties in the UK here. So the whole digitization of government data, of human data, of organization level data has increased the amount of data that's available on the web, on the cloud, available to organizations in general to process. And like I said, the advent of social media has changed everything. So now every minute there are millions of feeds generated on Facebook. There are millions of tweets generated on Twitter. So the amount of data that's being generated is more. I mean, we say we want to do real-time processing. It's the expectations from the system, even at the real time, it's super real time in that sense. So that is why, and that is how the whole term around big data came about. Now, moving on to the magnitude of data and what was and what is considered big in big data. So if we talk about 2010, in the Technonomy conference, it was just stated that, now that same amount is the amount of data that we've created from the starting of the civilization to 2003, in 2010, we were able to generate the same amount of data every 2 days, which was huge, and I think that has increased many-fold from that time to 2022. Going by the statistics, by 2025, we expected to have 180 zettabytes of data. Now, if you're not sure about the magnitude of how big that is, if you try and download all of this data, if one person tries and download, and you might have variable internet speeds, depending upon the area or the country or the place you're living in. But for an average person to be able to download that amount of data, you're going to take 181 million years. So it's practically not feasible for any human to download all the data that we have on the web today. Now, now that we know that the big data is big and it's evidently huge for mammoth-sized to be able to, for us to be able to process all of it in one go. The challenge with researchers and the challenge within a research community, it's a growing challenge. It's not something that's solved with the coming of such as Hadoop or Spark or Storm or any of those tools that are available right now. It's an ever-evolving challenge. The amount of data that's being created is growing. It's ever growing. And our capacity to process that data and our capacity to store that data is overwhelmed in every few years. So there's an ever-growing challenge for researchers, for the research community to come up with tools, to come up with frameworks that can manage this data beyond the scales of how it is being generated or how fast it is being generated. So if I try and put a very simple definition around big data, it would be and this is a commonly asked question, a commonly conflicted contradiction, I would say, that how big is big data? So how do you define big data? Now, for any organization, if the data that they're collecting, they don't have the infrastructure to store and process that data. So their existing infrastructure is overwhelmed by the storage requirements and the processing requirements of the data that they're currently collecting. Then their data, the data set that they have right now, is big data. So anything that overwhelms the existing infrastructure in terms of data requirements, storage, and processing is defined as big data. Now, a common chronological ordering of how to see how technologies have actually evolved over the years is given using the CERN journey. So CERN is a very famous laboratory, as I think everyone must be knowing, and pretty ironically, they are a lab that works on the smallest atomic particles, the subatomic particles, and research around that. So. And they are the ones who are famous for falling into the big data journey much earlier than everyone else. So that's quite a paradox that such a situation has been with CERN lab. Now, to look at the CERN lab's big data journey, back in 1960s. CERN basically worked with mainframe computers. So if you know what mainframe computer looked like, it was, it used to take a large amount of space. So their computer was housed in like a whole building. So that is the kind of processing capabilities and storage capabilities that they had back then. So data was typically recorded onto tapes. So and that the data recorded on the tape was then processed using a mainframe computer. Now, as the amount of data that they had grew, so they thought about, move, and technology also improved. So we had smaller computers, the size of the computer reduced with time. So they thought about keeping multiple computers and not just restrict themselves to a single mainframe computer. And which is when the whole idea of CERNet came into, which is like an internal network of multiple computers that could share data amongst themselves. Now, in the 1980s, internet popularized, and now people, wanted to access CERN data or the infrastructure at CERN, the data available at CERN. From within their own lab, which might have been in Europe, in America, anywhere in the world. So they no longer wanted to go to the CERN location to, access some very little information, which is pointless. Traveling that much for a work that small. So the internet brought about basically sparked a time or an age in which data sharing or infrastructural sharing could be enabled. And that was the vision that people had at that time, that, everything could be shared. And there was no need for people to travel across places just to access any bit of information or any bit of resources. Now, the infrastructural build-up on CERN led to what was called the evolution of the grid computing model, which they had put in place. So they had computers that were geographically set apart but connected to each other, so they could share information. They could not openly share information, but they could share information. Now, there are restrictions of the grid computing model, which quite majorly are around security. So you have, the data that's available on the grid is only available within the grid, and you can't share it outside the grid. That would pose security concerns to the infrastructure on the grid. Now, those restrictions were something that CERN wanted to overcome. And the next step that was taken in the infrastructural journey was to move to a more business-like model, which we now call cloud computing. So all the computers, all the systems set geographically apart could be accessed or could access infrastructure on demand, pay for the time that they use that infrastructure, and then let go of it when they're done. With all of the security, all of the privacy requirements, everything around compliances is taken care by the cloud service provider. So everything's off you. All you have to do is access something that's kept thousands of miles away from you, and use it till you want it, and then give it away. So that's how the amount of data grew, converted into big data. And the solution that they looked at was majorly a cloud-based framework of for management storage and processing of big data that they have. Now, looking at the hype around big data and why, what's the big deal if big data has existed for so long, and as we can see that the journey of CERN started way back in 1960s, and it's over the time to some 2000s. They could have something like a cloud computing model in place. So it's been quite a lot of time since then. So if big data has existed for so long, why is it that we're talking about it so much now? After decades of it being around. Now, there's a common metaphor in English that the sum is usually greater than the sum. The whole of something is usually greater than the sum of individual parts. So the reason why big data is such a big deal now is because now we know that there are very many domains and very many diverse sectors that can benefit from big data. So we have novel applications that have been innovated. We know of possible solutions that can be created for different dimensions, for different sectors that can benefit not just the business, but also the customers. So we've been able to understand the impact that this technology, just like the mobile technology, just like the virtual technology that we're using to connect to this webinar, the impact of these technologies are immense on not just one sector, but across sectors, which is why big data has become such a big deal now. Now, just to talk about the kinds of numbers around the kinds of data that we're dealing with. So on this page, you can actually find about how much of data is being generated by social media, for example, how much of data is being generated by Facebook or Twitter or internet connected devices or Internet of Things, IoT devices that are connected, with everything being digitally connected to the internet, practically everything being connected to the internet, from washing machines to the smart watches to even parking lot machines. So everything is practically connected to the internet. Now, what that does is everything is pushing data to the internet every minute, every second. And we've practically done datafication of the world in every way possible right now. So we have data that's coming from very many different sources, that is available in very many different formats, that is being collected by different kinds of devices, pushed to a common platform, and then unification of all this data to understand this scenario, all of it from a multifaceted aspect. From a multidimensional aspect, is what and where the challenge of big data lies. Now, if I try and give you an example of that, like I just said, the parking machines, the machines at the parking lots are connected to the internet. The cars are connected to the internet via the GPS. The traffic lights are connected to the internet using, again, sensors and IoT devices. Now, all of these can cumulatively be used to track a lot of, to monitor, to track a lot of information. For example, the number of cars that are that have visited a particular area at a particular time, or correlate that data with weather data. So as we try and correlate data coming from different sources, in this case, coming from cars, from parking lots, from weather. Now, this adds on to the already existing data that we are collecting. So now we are analyzing the data from cars and parking lots along with the data collected from the weather. So all of this increases the amount of data all the more, which is the challenge. Collecting data from different kinds of sources, trying to correlate them and come up with insights that that people had not initially or previously thought of. So that's the innovation in big data, and that is the novelty that big data brings to very many domains. So now, if we look at the research challenge around it, we have a lot of data, and we have a lot of data coming from a lot of devices, a lot of different kinds of devices coming in different kinds of formats, with variable quality. We're not certain if data coming from one single device is reliable, or it might have contradictory readings with respect to another device. So data with variable volumes, variable sources, variable formats, variable quality, being generated at variable velocities. Now, there are many different variables, as you could have already understood, that there are just too many different things involved, which is what the research challenge is, trying to bring all of this together to a unified platform in a way that all of this can be processed to give the kind of information, the kind of intelligence, or the knowledge base that's required from the system. Now, if we look at the more technical aspects of big data, then the traditional databases, if you go back to what were initially used and what is the kind of infrastructure that has been overwhelmed by big data usage, then traditionally we had traditional database management systems, which used to store row column format data. So any data, for example, that's generated by financial transactions, it's generated in a row column format, and we can put it in a normal DBMS and process it using SQL queries or MySQL queries. So that was the kind of infrastructure that we have. Now the data that we are generating, for example, now let's take the data from Facebook. You can post videos on Facebook. You can post audios on Facebook. You can just pictures, just text. And Facebook itself has a hell lot of analytics to do. So they have the number of views that are there onto a story, or number of times that a post has been visited, a profile has been visited. So all of those numbers around that as well. So you have text, numbers, videos, audios, pictures, almost everything that could possibly be generated in the digital world. Now, there is absolutely no way you can put all of this together and save it in the row column format. It's practically impossible to do that. Which is the main challenge around big data? Unstructured data. We do not understand the structure of the data that we have when we collate all the different kinds of data that we have collected from a device or a collection of devices. Now, in order to meet this challenge, in order to solve this problem around storing data that doesn't have a structure, frameworks and technologies have been developed. One of the big data technology, and one of the very famous big data technology, is Hadoop, which has served as the base technology for most of the other software or most of the other tools and frameworks that have been generated to solve different kinds of problems. For example, Spark, which is usually used for real-time analytics on big data, is a standalone framework that works on top of Hadoop. So Hadoop still remains the base technological framework for big data in every sense, and all the other tools and frameworks basically work over and above Hadoop. Now, if I move on to the next slide, now, just to give you a few examples to keep you on the same page, if some of you have heard about the amount of data that, for example, the human DNA has, and I think this has been a very publicized project, and every one of us knows that the amount of data that's there in the human body, if we try and collect all of that data and put it, that's also, it's in GBs. It goes in GBs over and above that. So now, if you try and decode human DNA, and for different kinds of applications, like, for example, find specialized medicine that for a condition that you might be suffering from. So the reason for your headache might be different from the reason of somebody else's headache. So finding the right medicine for the right person on the basis of your genetic makeup or your present body profiling, and combining all of that together to give you personalized medication. That's the kind of use case that big data fits into. Now, another common real world business perspective of where big data really helps is the example here is given of a shopping market. So now, if we combine the data coming from your location, the weather data, and the supermarket stock, then if the weather suggests it's going to be, the weather is going to be nice today, and the calendar data suggests that it's holiday time, maybe a Sunday or something like that, and if your location suggests that you are at that particular location in and around that shopping market, the shopping market, then they can probably provide you a voucher or a coupon code on a barbecue, and you're likely to take it because you might be thinking about a quick picnic somewhere or a quick get together with friends at home. So that is the kind of business use case that falls around big data. So basically using information from multiple sources, bringing it together to come up with something useful, something that can be helpful for a business, something that might be helpful for the customer, and both in all probability and possibility. Now, talking about the technical perspective of it, there are several models that have been suggested to understand and characterize data sets as big data. So how do we know that a data set, whether it is big data or not? I have a data set containing, say, 2 GB of data. I don't know what's the criteria, what's the checklist to understand that it's big data? Is there a benchmark for it? Now, there have been several models that have been suggested to help help technologists understand the benchmark and understand whether a data set can be characterized as big data or not. Now, the first one of this model, it's popularly called the multi-V model. They started with the 3V model, which was given by Gartner, and had 3Vs, as the name suggests: volume, variety, and velocity. Volume is the amount of data that's there. So how many GBs, how many TBs or petabytes or zettabytes of data do you have? Variety, what are the different formats in which your data is available? So is it just textual data? Is it textual plus numeric data? Is it textual, numeric, and video data? Or do you have audio data as well? Or do you have images? So what are the different formats or different types of data that are there? So how variable is your data? And then velocity is the rate at which data is generating in your system. So if we talk about the weather data is updated daily on a daily basis. If we talk about data related to the position of the sun, it changes at every moment during the day. So that data is collected probably every hour. Now, if we talk about health data of a person that's collected from the smartwatch, then that's collected almost in real time. So any changes to that can be tracked. If you have a smartwatch and you see your pulse trend, you can actually see it rising and dropping across different times in the day. So practically real time. Now, how quickly is the data being generated or updated by the system is what velocity is. Then this basic 3V definition was updated by IBM. They included something called veracity, which was to do with data quality. So how reliable is the data? How can I say whether a particular reading is correct or not? It might be a sensor failure, or the sensor may have miscalibrated. So quality of the data is something that was defined by veracity. Now, this has been updated by Microsoft to give the 6V model, and then in another research paper, they had provided a 9V model. So this is an ever-growing multi-V model characterization, and depending upon the kind of use case that you're working on, the model that you are expected to use changes. But still, the standard that we have is the IBM's 4V model, which is typically used to characterize a big data set. Now, this is just a graphical illustration around the 9V model, which is almost the latest one in research. So this gives a more business perspective of it. So how valuable the data set will be from a business perspective. Will it improve the visibility of the business? What is the kind of variability or different dimensions in the data? And the validity of the data from a timescale perspective. So all of those different reads are also included in this model. Now, if we look at the big data value chain from the generation to visualization, which is analysis or visualization, then generation of data, as I think is pretty evident from the discussion we've been having for some time now. Data is typically generated from any digital format of data that's available within an organization from outside the organization. So if we talk about the university is generating internal data in terms of student data, data of their employees, data of any non-teaching staff that they have and the teaching staff they have. And other than that, there are external data sources as well. For example, social media data. Every organization has a Facebook page and an Instagram page, and they go live with sessions like these. So of the data that goes on external sources would be external data to the organization, but still data that's related to the organization. So these are different kinds of sources from which any organization generates data. Now, how do you collect all of this data? Now, from an organization or any use case might be collecting data from all of these or might be collecting from one of these. Now, web crawlers typically collect data from the internet, network monitoring system. So if you have an intranet or which is eventually connected to the internet, any data that is collected related to network activity falls into that. Then any log files, any sensor data. For example, if the most common sensor data that's collected these days is the weather data or the traffic light data. Now, this data, which is collected, is transmitted to a system where it needs to be processed and stored. Now, do we need all of that data? Can we filter some of the data out and reduce the size of the data just to make sure that we are not processing data that we don't really require? So pre-processing is basically a kind of a prerequisite to storage and processing, where we try and clean the data, improve its quality, filter the data that's not required, and just put the data that's required, and identify the exact requirements of the use case, identify the data that we require for that use case, and push that for storage and processing. So that's the pre-processing step. Then storage. Now, there are a lot of NoSQL solutions that are typically used for big data storage. So Cassandra, MongoDB, HDFS, which is inbuilt in Hadoop, and Google File System, which is actually a precursor to all of these. So the first NoSQL database solution that was provided was the normal RDBMS that we have, because normal RDBMS does not support unstructured data. In order to support unstructured data, a new class of database solutions came about, which are called NoSQL solutions. Now, the list that you see here are all NoSQL solutions. GFS, or Google File System, was the first of these, and the more recent ones and the more commonly used ones are MongoDB and Cassandra. Now, it really depends on the use case that you're working on, but MongoDB and Cassandra generally fit with a lot of use cases. Then the final aspect here, the final a loop in the chain, is processing and analysis, which involves a statistical analysis, data mining, text mining, many new technologies like natural language processing, social media analytics, or there are many different kinds of statistical tools that might be put into place, like univariate analysis, bivariate analysis, multivariate analysis, depending upon the use case again, and depending upon what you're trying to achieve from the use case. Now, the process flow from a technological perspective is the data is created, and initially it's just about bringing all of that data together. So say you're generating data from 100 sensors, you will have to collate all of that data together and try and make sense out of the collected data before you can send it for feature extraction and selection, which is a very common data mining process flow if you've seen that. So the big data process flow is not very different from any data mining process flow. It's just that the scale of big data process flow is much larger, while data mining works with much less data. Now, once this data has gone through feature selection, feature extraction, so we know the features that we're working on, and we know what is the data we're working on. We split the data, train the model, validate the model, and finally provide a visualization around it or an analysis around it. So that's the whole big data process flow. Now, coming to some real life use cases, the general hierarchy of how the data science paradigm basically looks is very much like the graphic that you can see here. So data is a lot of information. So if we go back to the school level definition of what data is, it is raw facts. So they're just facts, raw information that's not really making sense right now. But when we take it to the information stage, where we pick data that's relevant, we convert this data into information. Now, when we install something like or deploy models like data mining, etc., we convert this information into knowledge, which is then as I think you would already be knowing, is used to make predictions, etc. Then using artificial intelligence and modeling of predictive models, prescriptive models, descriptive statistics clubbed with all of the others, we create what's called intelligence. Now, this is what the paradigm currently looks like, with research being worked upon in the direction of taking it further from intelligence to wisdom. Now, what that would include is it would include the intelligence that comes from artificial intelligence and experiential learning that will also be, inculcated in the systems, like humans. I mean, humans have, like it's commonly said, that, with experience comes wisdom. So as the system interacts with the environment, with humans, it'll have its own sets of experiences, and from these experiences it'll learn. So that's what experiential learning is all about. And this experiential learning, along with the intelligence that it has from artificial intelligence, which is historical data analysis, the system will gain wisdom in due course of time. So this is how the paradigm is basically growing. So we have data, information, knowledge, intelligence, and which will in the future move to wisdom. Now, if we look at the use cases, some basic use cases that are typically there is, as you can see here, this is basically a logistics use case. So a common example would be you order something on Amazon. Now, while you've ordered something on Amazon, everything, you must have seen that sometimes, Amazon can provide a delivery. If you order early in the day, they can actually provide a delivery by the end of the day, or just the next day. So how is it that they process everything so quickly? They process everything so quickly because everything is automated. Everything is already driven by a lot of data. So the inventory management makes sure that if they know that there's a demand for a particular product or a particular kind of any specific service, they have that in before somebody orders for it. So the whole inventory management, the whole logistics management, the whole process that's followed during the supply chain of you ordering something to it being going to the nearest delivery depot, to the product coming to the nearest delivery depot and being delivered to you. The whole thing is automated in such a manner that it minimizes the amount of time that it takes for them to get the product to you. And that's how, all the different aspects of the supply chain and logistics have really improved with the incorporation of artificial intelligence and data science. Now, another business that has really been impacted is the telecom companies. Now, a very common statistical analysis that's, if somebody is from a statistical domain, then a very common kind of statistical analysis is called churn analysis, where you can actually from data you can find out, from a telecom perspective, you can actually find out which of the customers, if you have a list of customers in a specific demographic location, let's reduce the scale, then which of the customers on the list of customers that you have is expected to leave you and teleport the number to another operator. Now, how this analysis, how does it help the telecom operator? So the telecom operator knows that there is, say, in the 1 lakh subscribers that it has in a particular city, 10,000 customers are expected to leave the company. Now, leave the operator and choose another operator. Now, there are two things here. One, the operator might want to look back at why they are choosing another teleoperator. And second is, launch a scheme or, give them offers which can avoid any churning out of customers. This is not just a telecom use case, although it's very commonly used in telecom. It's commonly used by other businesses as well to understand if a set of customers is moving away from their product or their brand. So brand analysis, image analysis, all of this from business perspective is based on this particular analysis. Then finally, business intelligence, which is a much talked about, pretty saturated research field now. where a lot of solutions have been developed to understand market segmentation, to understand which demographic location, which age group, which kind of customers might be the right customers to target for a specific product, and then you target that specific set of customers using social media or other marketing campaigns to increase your revenue, increase the turnover for a particular product. So that's one aspect of it. Then the organization aspects of it, for example, it might be used by the organization internally to reduce employee attrition. So to understand why their employees typically leave them to join other organizations, what are the possible reasons, come up with solutions to help them resolve their issues and reduce attrition in that way. So these are some of the use cases. Some of the commonly and very, very rapidly growing use cases of big data are in manufacturing. And one of the most popular ones around it is predictive maintenance. So there are sensors deployed in all the different equipment that are there in a smart factory, which is like moving from Industry 4.0 to Industry 5.0. So the whole factory will have sensors on the conveyor belts, on the equipment, and they will be reporting data back to a common server. Now, analysis of this data will help us understand which of the parts is expected to wear out sooner and when, with a percentage of error, but when is it expected to wear out? Now, what it can help you do is it can help you plan for the future. So if you say that say equipment number X is going to burn down in 10 days, then you can order a maintenance schedule and spare parts for that machinery and get it replaced in due course of time just to ensure that the factory operations remain unaffected, so that the order delivery remains unaffected in turn. Now, this is a graphic around that, around predictive maintenance and how it's related to production and maintenance. It's also related to the distribution data. So you have to ensure that the downtime is minimum, and also to the supply chain data. So when you're sourcing spare parts, you are accessing a supply chain and your data analysis should make sure that the spare part is with you right in time. So not before time, because if you get it before time, you'll have to store that spare part. Usually, when we're talking about factories, the spare parts are also huge. So storage space for them becomes an issue. So it should be right in time for it to be used and not late enough to miss the maintenance schedule. So right in time. Then another common domain that's majorly impacted by big data is healthcare, and there are, as you can see, a lot of applications. Each of them are research areas in themselves, from medical imaging to self-harm prevention, to developing new therapies, to precision medicine, predictive analytics around it, improving patient interaction, and now with COVID-19 hitting us so badly, telemedication, interaction of the patients with medical facilities, improving the operational efficiency of the basic emergency services like ambulances. So all of this is something which revolves around data science in one way or the other, and it just requires a bit of innovative thinking to come up with something that has not been thought out yet. And as I think it's usually said in businesses that normally the most path-breaking solutions are very simple problems that nobody thought about. But solving those very simple problems in a way that it benefits a very large audience is what makes a business and a data science business, from my perspective, successful. Now, these are a few other use cases around this. It's being used big time by political parties to win elections everywhere in the world. It's used for surveillance by most of the security agencies. With the whole CCTV camera network that we have around us, if they want to track you down, they can actually track your footsteps too, if they want to do it. Then it's used in sports. Sports analytics is again a huge area of research now, where you can, you make predictions on which player is going to perform well, which player is not going to perform well, who's going to win a game. Majorly used by a lot of used for betting, etc. Now, from an entertainment perspective, artists use data science for understanding what are the listening preferences of their audience, and updating their playlists accordingly. One of the areas which is really upcoming, and something that's been actively worked upon, is self-driving car, because it uses a lot of technologies and it's a very challenging research problem. So self-driving cars is something that's really coming up, and it's, from a research perspective, is very, very active right now. Then we talked about supermarkets and hospitals already. This is a small video, and I don't think if I have the time to play it, so maybe I can share it, and you can have a look at it later. Now, this is my book on big data, so big data and analytics. And if you want to know more about the technology, or it's like a beginner's book. So, in my experience as a faculty, what I have understood is that big data or any new technology is generally because internet today is the main source of information for everyone. So videos, tutorials, blogs are the main source of information. But then collating all of that information together to create a sensible learning curve is something that is where students have a problem. So this book basically covers all the different aspects of big data and Hadoop and the practical implications of it. So setting up the system, to running programs, to running tools onto those programs. So all that is covered as part of this book, and you can contact me if you wish to get a discounted copy of this. And that's all for me. And if you have any questions, I'll be happy to take them.
Participants, do we have any questions? You can speak your questions, or you can also put it across in the chat if you have any. I hope I'm audible to all of you.
Yes, you're audible to me at least.
All right. Participants, do we have any questions? Anything that you would want to know more or ask Dr. Samiya? Okay, I think we do not have any questions in the chat box. All right. Okay. So that was indeed a very insightful and knowledgeable session for the participants, Dr. Samiya. I'm sure. So these are, most of the participants are already into data science, they're learning data science. So they're aware of, these terms. So I think they did get a very deep insight, and especially the use cases. One thing that I would want to share on my behalf is would be, as for the participants, you've shared across many use cases that you spoke about. So if they want to work on the real-time use cases, so how can they go about that? Because that is some challenges that they face when they are about to find a problem statement, or select a problem statement for their project, or any research that they would want to work on. So that is something I would want you to guide them, if you can guide them across in like just 1-2 minutes.
Yeah, I mean, that's a very common question that I get. I mean, how to pick a problem, how to find a research problem. Now, most of us are doing, innovation, and the times of invention are long gone. So from my perspective, that's what I tell my students, that in order to find what can be done, you need to know what has already been done. So until you don't know what has already been done, there's no way you can find out what you can do about it. So if you look at existing research or existing things that have already been done, and you understand from a use case perspective, you need to understand that industry. For example, if you talk about use cases in manufacturing, you got to know how manufacturing basically functions to be able to, understand what's missing in their use case. Now, a lot of responsibility of that, I think, falls on the faculties as well, to have collaborations with industry partners or somebody who can, help you guide through the actual workings of the industry. But then, in case that's not there, then also there are a lot of research papers that the work that have open data sets that you can use, and there are a lot of existing research that has been done in almost every domain. So it's nothing's nobody is waiting for the apple to fall nowadays. We are all working on existing research. So if you read, and you will have to read a lot, that is only when you can think enough to innovate. Does that answer your question?
Absolutely. I think you mentioned it on the point. That is something that the participants struck that has been already done. So yes, with this, I think participants, do we have any questions from your end? Okay, I think we do not have any questions. So with this, thank you. I would like to thank you, Dr. Samiya,
Thank
for
you.
coming and for your time and coming and sharing your experiences and your work that you've spoken about. So thank you. We had a wonderful session with you, and we hope we do have many more sessions. So those who are attending this session for the first time, we do come up with such sessions ahead also, sessions from the expert industry persons. So do attend, and thank you everybody.
Thank you very much. Thank you
Yeah,
for having me.
thank you, Dr.
Right.